Hi, my name is Vladislav Manly and I will present our results in HomeRobot OVMM challenge. My teammates are Volodymyr Kuzma and Ruslan Partsey, and we are Team Kuzhum from Ukrainian Catholic University. Here is a short agenda for our today's presentation. We started that competition with EDA of the task. After examining the proposed paper, HomeRobot Open Vocabulary Mobile Manipulation, we outlined that perception is a shared feature for all our tasks, and its improvement would yield positive outcomes across all tasks. Besides, the place task experienced the most substantial decrease in success following the transition from ground truth to DATIC. As it is the last skill and the success of the whole episode depends on it, we outlined place as one of our main priorities. Here is a closer look on change of task success with change of perception. We can see that place is overall the worst performing task, though it is very important, as its success defines if we passed or failed the episode. Also, from the plot we can conclude that it is very dependent on perception. Thus, we understood that improvement of both place and perception may improve our overall success rate by a considerable amount. As our primary evaluation metric is overall success rate, and our resources were insufficient to try retraining all tasks or creating new solutions, we decided to focus on those two tasks, perception and place. Let's look at the agent's architecture to understand better how it completes the task. High-level heuristic, the one in the green box, goes low-level skills in a loop step by step, switching to the next skill when the previous one is terminated with stop or grasp action. The only change we made to this heuristic compared to the baseline is a condition after terminating the pick skill. It checks the grasp center, indicating whether an object is held to start navigation to receptacle in case of successful pick, or return to navigation to object otherwise. Low-level RL-based policies have a very similar architecture, with depth, semantic segmentation, and RGB frames passed through convolutional neural network, while other sensors measurements, like position from GPS and compass, or binary value from the already mentioned grasp sensor, are passed through a fully connected layer. Later, all features are concatenated and passed to RNN, LSTM in our case, to obtain action and a new hidden state. As mentioned, one of the significant improvements was the change of perception model that creates semantic segmentation from RGB frame. So let's look at this architecture. The baseline implementation of agent used DATIC for both detection and segmentation of receptacles and call objects in the frame. In our agent, we implement an identity pipeline with an additional segmentation block consisting of YOLO version 8 for the generation of bounded boxes and mobile SAM prompted with obtained boxes for segmentation. The resulting masks from DATIC and YOLO SAM blocks are overlaid with higher priority for YOLO SAM masks. During place training, we had two sources of insights for the approach: analysis of agent evaluation on validation scenes and analysis of metrics gathered during training of place with different configurations and rewards. The first approach was based on watching agent replace and observing errors made during evaluation. With this knowledge, we could understand where we have flaws in agent's decisions. In that example, we can see that agent closed his sight with his arm. The second approach was applied during fine-tuning of place. We couldn't afford to retrain the whole task. Thus, we took the present checkpoint and started looking for the best configuration of training parameters and rewards that would result in place improvements. With those two approaches, we found a reward in training configuration that improved our place success after fine-tuning. Here we can see the results of different methods for OVMM task. First two columns show which perception method or place we use for specific evaluation. All other columns show success rates of a task or episodes. In the top row, we can see the approach with DATIC perception, which was implemented by OVMM team and was a baseline for us. After implementing pure YOLO SAM perception, we improved partial success rate, though the overall success rate worsened. But after combining it with DATIC perception, we significantly improved all metrics. Further use of fine-tuned place checkpoints improved the relative success of place, thus improving our overall success rate. We managed to improve result of baseline agent by more than 4% of overall success rate and by 16% of partial success rate. As of today, here's how the public leaderboard for test standard split looks. As you can see, we are now placed first, with a 0.8% lead in overall success and a 0.5% lead in partial success metrics. As the evaluation of the second phase would be done in the real world, we were eager to test our perception in a non-simulated environment. Thus, we shot several videos, which were then processed by our segmentation for receptacles. In general, we got a pleasant result for a handheld camera. Thus, we hope our approach will perform well at real-world simulation too. After participating in the challenge, we still have a list of ideas that can be implemented on top of named solutions. We can outline next possible improvements. We analyzed what objects were used for our training episodes. Scenes for OVMM tests are composed of objects from the HSSD dataset. That dataset contains thousands of different assets, but we discovered that a lot of them were not used in episodes. That is why we suppose there is still a possibility for improving our perception model by utilizing a more diverse training dataset. In perception, we can use tracker detection, which would predict each frame with previous frame's information. That would make our predictions more stable over the episode, which can positively impact the whole OVMM task. Besides, we are sure there is room for improvement in skills and high-level policy. Our current policy was a heuristic sequential call of skills based on the metrics. Some neural network-based models may perform better with executing skills at the optimal time, also having the possibility to run previous skills. In conjunction with policies, we outlined skill improvements. We tested new checkpoints from HomeRobot version 0.2, and they show visible improvement compared to our checkpoints. Last but not least, we are thinking about better volume representation. Our solution only has LSTMs that pass data to future states. It has flaws, because we may forget the data from the start of the episode. That is why volume representation may help. Proper information saving may help eliminate senseless backtracking and improve navigation, though training the model with the data is computationally expensive. That's all from us. Thanks to the Habitat team for organizing that competition.